有没有？Hello, we are Group B, and this is our overview. And this is the problem. The problem is the load of the middle of the base plate is too large. Previous people tried to add metal balls under the middle of the base plate, but it will cause another problem. The problem too is the weight of this system is too heavy, so the metal ball will break in the floor. So we think the main problem is the problem one. Just add metal balls is not a good solution. Let's see the review. We did some research on several AMR robots on the market, like Kuga, MSI, and Qubit. We found that the area and the height ratio are way smaller than the current model, even with the heavy-duty robot arms. We think this design is mini, so we will redefine the structure in origin robot.
So this is the paper we found that it talked about the sinkage of the road after the track unit go over it and also a wheel unit. This one is the wheel and this one is track. As you can see, for the sinkage of the wheel, it goes over like around 11 centimeters, and for the track, it's almost like only 5. So we think that if we change the track unit even without the metal ball, there's not gonna be like a less likely like the unit is gonna break the floor. So the solution we came up with is we changed the wheel unit to the track unit, and the second solution is that we add up another layer to the AMR system. So let's talk about our model. This one is the control group model. This is like a simplified version of the original AMR model. We add like this small block here. This small block is a representation of the robotic arms because it's simpler that we just add a block and then give it a weight of 550 kilograms and to demonstrate the force acting on the base plate. And this is the clamp that we made to simplify the motor system and also to connect the wheel and the shaft to the base plate. And this is our treatment group, which is our own model. So the first thing we do is to change okay, so this is our track unit. So what we do is we have these two and these two wheels. We connect it to the motor, and this two is only to a supporting shaft. So only these 4 wheels is gonna move. And this two is not gonna move, but it doesn't have a motor on it. It's just a supporting shaft. And for the first system, we didn't have these 2 supporting wheels, and also the track. And also by the moment, we know that if the distance between the middle point to the wheels is further, then there's gonna be more moment, and which will cause more force being exerted on the base plate, so resulting in greater deformation. And to adjust this issue, we add up another layer, this layer, as you can see here. So we can move the wheel unit much closer to the middle point, like this, more tight. So it's way much closer to the middle point. That means we can have better support of the base plate and better weight distribution. Okay, so then we add up this kind of tilted beams, support beams. So by adding this is the front view of the model we made, and this is the side view. So by adding these support beams between the base plates, we can actually improve the structural integrity and the distribution of the forces. Because like by tilting these beams, we can have the forces not acting downward, it's acting like sideways. So we by this design, it's kind of enhance the way we deal with the stresses and the load concentrated in the middle.
Result. The colors are irrelevant to the magnitude of stress and strain. It is just the distribution of numerical values. Stress distribution analysis for the original model. The upper left. The maximum stress is 385 kilopascal. After we place the track wheel on the bottom of the base plate and add brackets to disperse the stress, the maximum stress is reduced to 305 kilopascal. And we can find from the strain diagram that in the original model, the deformation caused by the stress is concentrated in the part where the robot arm is connected in the middle. The added support beams and the track unit under the base plate can disperse the stress better. As we can see, the red deformation displacement is no longer concentrated in just one point, and the maximum deformation reduced from 0.061 to 0.12. It greatly reduced the bending deformation caused by stress.
Now let's move to the conclusion. As we can see that the initial design of this system faced some challenges related to the weight and the load distribution, leading to some failures, which is in this case is breaking the floor. And to handle this issue, some redesign modifications are implemented, including the use of track units and additional beams, and also the layer is added. And as a result, the stress and strain applied on the AMR reduced significantly by increasing the contact area with the floor. The track units effectively distribute the weight, reducing stress on the floor and also preventing damage. That's all.
First, have you calculated the overall weight of the existing system? Overall load of the existing system.
The load of the
Yeah.
What do you mean by that? You mean by
Total load of the structure which the wheels are.
So you mean by the
Which type of stress you have analysis? This one myself? Which stress you have analysis?
which stress?
Yeah.
So this is the whole system, and then we add the weight in the middle.
But have you seen the actual one? The weight is distributed. There is some battery.
And there's
system.
some battery and some
Yeah.
motors here, but we think that's not the main problem, because the main problem is the heaviest thing. The robot arm is almost like 500 kilograms,
Yeah.
and then the battery is like 75 for each. So it's not that. Oh no, the motor is 75
Each. Yeah.
each, and
The controller and the battery.
the controlling box is 100 kilograms, but we didn't add it here because I think if we can just like we focus on the main issue because
But in this case, your height is increasing.
which one? You mean
The
our
case,
system?
your system, your height is increasing.
Yes.
So how you can manage the robotic arm, because they have some positioning why they made it like this. And your plate is like completely metal you have used, or there is a
Aluminum.
like
We use aluminum for our.
how aluminum can sustain? It's a steel in existing condition. It was steel in that case.
Yes.
In actual case.
And the
But why you
frame
use aluminum?
the frame we use is steel, but the plate we use aluminum because it's lighter.
But why we use plate instead of a different arrangement without a complete plate? You can just use some bars to connect it. Why you use complete plate? Because you have to install robotic arm,
Yes.
you need a space,
Yes.
so you have a complete plate. Why
Yes.
we use complete plate?
Instead of like a module that we end up.
Yeah. Because that is your chassis, actually, the bottom one.
Yes.
The up structure, why you made like this? My
Up
question is-
structure. Because the current structure is like it's like the left one. Is this one, right? It looks like very similar to.
Actually, the base plate is enough to sustain everything. The
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 upper
current
base.
structure is only to make it a compact design.
Yeah,
It's
yeah,
not
we-
it's not bearing any load.
Yeah, we know that, we know that.
Yeah.
But because the version beside the top plate have like a hole, and
Yeah.
then the robotic arm is actually on the plate under it, right?
Yes.
But for just for simplification, we just add it up here because it doesn't matter if we put it up or if we put it down.
So which because the base plate is not looking like how you manage like whole complete structure with thick plate. What is the thickness of the plate? Is the same as which is right now?
Yes, and also the width and the
Dimensions are same.
yeah, the dimension is the same.
You should, in report you should be perfectly aligned that it is the existing condition, what are the dimensions, and in your case, you have to similarly manage the dimensions.
So we didn't put the graph on here.
And which type of stress you analysis? Or you use in ANSYS?
Oh, we're using Inventor,
Inventor, not ANSYS.
not ANSYS, because we didn't have.
So which type of analysis does Inventor do? It's a one Mises stress or which stress? Or principal stresses? It's a one Mises stress? One Mises. You study it in the DMC class, stress. Principal stresses come total stress, one Mises stress.
von Mises stress. We also do a von Mises stress, but we think the graph is actually not like this significant because
You
the
have
whole
to
thing is
showcase which
everything.
type of stress you are analyzing on that.
Everything.
Is it what are the principal stresses, what are the conditions, what are the values?
So wait. So this is the von Mises stress. The point is is here. Only the shape have.
Actually, you have to put all the specifications, all the values.
All the values.
Yeah, like battery, controller, everything, every loading. Then only you will get actual stress on the each wheels or each shaft.
We don't really have the dimension for all the parts.
You can get the dimension. You can put the dimension. The one.
Yeah, they have. Or
I will share you, maybe in the report you can present it very well.
And this is like the base plate dimension is the same.
Do you want the
as
dimensions of each?
No, this one is the base
No,
plate
if
dimension.
I can give you the dimensions of each,
But I don't think we have time to add up everything.
but you can add like, just you can change it and just in the report you can add the dimensions. You have 1 week of time to complete the report.
You mean like the Word report or?
Yeah, you can add more loads on that. Because it's only the robotic arm of how much kgs you have,
500.
but there are many other items which maybe have an impact on different parts.
Yeah, but the initial problem is that the load in the middle of the base plate is not like other part of the base plate is having problem, only the middle. So we are trying to fix this problem by just focusing on the middle of the
So
base
this
plate.
is the one matter stress you have shown me.
You mean the one, the blue one?
Blue one?
Yes.
Okay. It doesn't give any, only the portion affecting is the shaft.
Yes, only the shaft.
So in your case, it is reduced to 300 and how much if your total overall load will increase
You mean
in this condition and in that condition?
the total?
By installing the track system, how much total load will increase?
Total load will increase.
Yeah.
Because adding up another wheels and the shaft will increase
Yeah.
the weight, right?
Right. So my question is how much it will increase? Because you design it. So inventor just calculate the load if you put some details. Have you calculated the load of this one? Total load?
Total load,
Hmm?
you mean the whole system?
Yeah.
Without the
Yeah.
robotic arm? We didn't calculate the total load of the system, but we think by adding another wheels and also the track unit,
Right, correct?
it's gonna have more contact area, so
So
the
that you
adding.
can just present in your report that total load is of your unit. Okay? Okay, thank you.
Hi everyone. Hi Dr. Patel. Today we're going to present our final report for the OAMR robot for inspection, the improvements that we've made into the system. So just to do a little recap for what we're doing. So the AMR robot is like a box that has a vertical axis and horizontal axis, and what we were doing is redesigning the horizontal axis. What it is a platform, a metal platform, with a gripper moving along it. So, and why we're doing it? We're doing it to first make the design sufficient to work with higher loads, because the original robot was designed for 10 kilogram rolls of flexible PCBs, and our goal was to design it to suffice the requirement of 50 kilogram rolls and to simplify the system. So here you can see the final model for our design. So what you can see here, this here we call the base plate with everything installed on it. Here is the dovetail connection, which is used for as a guide for the arm body. This is the arm body on which the gripper is mounted. This is so-called worm gear with a driving gear set and a motor. Yeah, so maybe if you remember or if you don't remember, so this is the model of the base plate that we presented to you during the progress check, the progress report. So what's changed? The only thing that has changed is that we added some honeycomb-shaped holes into the base plate in the regions of less stress concentration to reduce the weight. So this is only for weight reduction. It's not much, but I guess it works, and it's an improvement compared to the original model. Yeah, here you can see larger on the photo. So we don't change anything in the Z vertical axis. It's the same bolt screws, same as the original model. Yeah, all our changes are concentrated on this base plate.
Okay, I'm going to take a responsibility for this part. So to continue from what the group is saying, this is just a total information about it. So we do the same test as last time before, so this is just a picture about it. Okay, this is also we will conclude this later. This is also the maximum principal stress. Okay. Actually, I should add the original value from the Dr. Patel's research, but sorry about the space. We don't have that much. So this is our last time that we present the safety factor. So basically, we just pump the honeycomb to reduce the weight. Just that for this base plate part. Yeah, as you can see that it's pretty much that it's the safety factor is like doubled of the value. Okay.
So for the new design, we lower the safety factor and remain the safe range to not over design to handle the load without risk of failure.
And here about the arm body. So as you can see, here is the first model, not the first actually, but our final arm body model for the progress check. And here is the further improvement of that model. So what we've changed. So those triangular kind of shaped holes for weight reduction, they became bigger because that model had like very, very high safety factor. I'll show that later. And also, so we made them bigger and we added another cut here, and we also reduced the thickness of this thing here, of like the facing the face where the gripper is mounted. Yeah, also change the thickness of that. So this is probably as light as it can get. I mean, in this model. Yeah, please. Yeah, so here it is with all the dimensions. And here is the ANSYS analysis that we did on this model. So as you can see, this is the total deformation of the model. It's pretty well distributed along the entire model. So I think this design is, I'll say, I think it's not the worst design that you'll see. Yeah. Here is for one mixed stresses. And here's for maximum principal stress. So here is the comparison between our first model versus our current model. So what you can see, we could reduce, by reducing the weight and cutting the holes, we we reduce the safety factor by 100%, yeah, of the new value. So it's like a half of the old safety factor. Yeah, and to conclude it, by developing the design, we could reduce the safety factor to, I'd say, more or less optimal values. It could be less, but I think it's all right. Yeah, especially considering that it's going to work alongside people and for people's safety. I think it is vital and crucial to keep the safety factor high enough so it doesn't hurt anyone. And
this is the specification for the gears on the motor and the worm gear itself. So now for the motor power and torque, since the original design uses a 1.3 Newton meter torque servo motor, so if we assume that the load is 500 newtons with a torque equation relating the gearworm to a pulley, the gearworm has a diameter of 20 millimeters, and since the servo motor will be attached to a gear with a gear ratio of 4, we got a result of 2.5 Newton meters, which means that the original motor is not sufficient enough to drive the gearworm. However, in the power calculations, assuming that the speed of the gearworm is the linear speed that the gripper will move is 1.5 meters per minute, and then converting it into radians per second gives us 24.5 watts. So for the new motor, we found this on the internet, which is 2.8 Newton meters, and then capable of 1500 RPMs and up to 400 watts, which will be sufficient to drive the new design. Thank you for listening.
So, can you show me the back one, like mobile?
the entire thing.
No, no.
This first test.
Yeah, this back. Yeah. So where do you apply the total load?
I think it's like as far as I know, the entire roll is like 60 centimeters long, is it?
Mm-hmm.
So the load is applied around 40 centimeters apart from the
Here the gripper will attach.
Yes, yes,
and
yes.
then you apply the total load on.
Yes, so taking the gripper length into consideration,
Consideration.
yes, then it's like here. So like 10 plus 30, yeah, it's a remote force.
So there you applied 50 kg.
Yes, 50, yeah, 500 newtons, yeah.
500 newtons.
Yeah.
So 50 kg, and this analysis on basis on that.
Yes, yes, exactly, yes.
Okay. Does it work?
That's it?
Yeah.
Thank you.
So I asked Group B. They show the total stress results. So you have to showcase in that way. What analysis actually you are doing. Von Mises stress, you can show the total stress value. Yeah. And this way. Okay? Just don't show it like 300 K 5 kilometers. Just showcase this type of in report. Okay? Yeah.
Hello everyone, we are Group A and are 3U tube state design and analysis. And this is our table. Okay, first thing we will talk about the tube state body. This one. This two is the solar panel, so we just analyze this one stress. And our material is aluminum 5052O, and this is our basic information. And
elastic modulation ratio, like that. Okay, first thing is static load analysis. Because the CubeSat developed like this way, so we think the load will act like this way. So this is how we divide the total load, like gravity, inertial force, and air resistance. And the mainly load is from air resistance, and this is how we compute. And this one is the worst condition. Like the velocity is 2,000 meters per second, and yes. So this one is the maximum load it will encounter. And this one is free body diagram. The base is the fixture and the load is from here. And this one is stress analysis. Here is the maximum strength, and the pharmacist stress is the like 3.4 times 10,000, yes. And this one is very low, like 6.2 plus times 10,000, yes. And this animation is about displacement analysis. And here, because this field is the picture, so the displacement is approximately 0. And here is the maximum displacement. And here is the safety factor analysis. The minimum safety factor is here because the above stress analysis here have the maximum pharmacist stress. And how we compute the safety factor is use maximum pharmacist stress. Okay, next one. And next law we will discuss the sinusoid load analysis. And this table is from the paper. And here is our setting. Like here is G, the gravity, and here is the frequency, and here is the how to say that? Like here amplitude. Amplitude, the unit is the amplitude, the unit is G. So here is how we divide. And here is free body diagram. Green part is also the base, is the fixture, and purple part is the sinusoid load. It's from up and down because it's it will have the positive and negative amplitude. Yes. And stress analysis is here. Actually, because we use the SolidWorks simulation, so it will separate to 60 states. So 60 states will have the different frequency, and first state is about 5 hertz, and 5 hertz the maximum stress is like this, minimum stress. And here is the 16 state, and the frequency is 100 hertz, the maximum frequency we use, and the maximum stress and minimum stress. Okay, and next part is how we compute the safety factor. The safety factor we use the EOLI criteria. Here how we compute, and we assume the sigma m and tau a is 0 because we divide the whole stress is about the amplitude, and the mean stress is 0. So pharmacist stress for the mean is 0, and pharmacist stress for dynamic is sigma a. And here this one is the time, not x. Sorry. And here is the sum of the whole state, like 1 state to 16 state, the amplitude. So the the final answer is 166.1. And we think this design is too safe, so maybe we can reduce the thickness or something. Yes. And next part is the random load analysis. The free body diagram base is the fixture. Purple part is the here is random load. Sorry. Random load is also the upward and downward. And here is our setting. It's also the G, and here is the frequency and the amplitude. And next up. Also, this is the stress analysis. The maxima is 1 point here, and minimum stress is here. And this one is also the displacement animation. And here is how we compute the safety factor. It's the same like the sinusoidal load. And the final answer is 625.43. And actually, the sinusoidal and random load safety factor is seems like too big, but actually these three loads maybe will encounter at the same time. So maybe safety factor will be lower than this simulation. Okay, next part.
Okay, then let's talk about our solar panel. There are two different solar panels. One is the conventional folding solar panel, and the other is the origami inspired solar panel. And we will comparison those advantage and disadvantage. And first is the design complexity. Conventional solar panel is lower cost, and the origami inspired solar panel is higher cost. And second is the fold volume. And conventional folding solar panel is much larger. Like you can see the animation of our conventional solar panel is bigger than it's much longer than the origami solar panel. And third is the deployment reliability. Conventional folding solar panel is much reliable, and the application conventional solar panel is used to simple equipment or ground use, and the origami solar panel is used in spacecraft, deep space exploration, and portable device. And the material of the conventional folding solar panel is used standard materials, and the origami needs to use the more flexible materials, so the cost is much higher. And here is the animation of our the left-hand side is the conventional solar panel, and the right-hand side is the origami solar panel. And we also made a paper model of origami solar panel like this. And it will fold like this. Like this.
And next part, and this is how we design the solar panel. And here the original shape is the hexagonal, yeah, hexagonal. And here is the line to what's that? Extend this size. And here this blue line is the bisector to let this two angles the same. And here the first step is to connect these 2 points and let the line to connect this one and across the red line to another blue line, and do the sensing for your maxima area. Yes. And the right part is we do the real CAD file in the SolidWorks. Yes.
So the application for both solar panel, for the rectangular one, the conventional one, be used for ground-based equipment, or cost-sensitive project equipment requiring frequent maintenance, and for simple outdoor charging devices. But for the origami one that we focus on, the application for it is for spacecraft and satellite, deep space exploration mission, and ultra portable equipment, and for high-end innovative applications.
And this part is for the power generation, and we do the comparison between two origamis. And I just assume that the power generation under the same dust optical depth. And dust optical depth is kind of a measurement that the light would like attenuate or absorbed by the medium, like the dust. And the same temperature, light intensity, incident angle, and cell packing density. So for the daily energy output would be like 20.83 to 25 watts per meter square. And the dust accumulation loss would be 0.4% to 0.5% per solar day. And it is before, like the left and bottom one graph is before the 20 solar days. So we just do comparison between two models. For the rectangular model, would be the area would be 0.156. This one is just one solar panel on the folding model, but we put the 3 at each side. We have 2 sides, so we have 6. So we just keep the length of the hexagonal model is same with the 3 rectangular model. So the area would be hugely different. Like the area for rectangular is 0 point something, and the hexagonal one would be 2.8. It's 20 both times. And the daily power would be huge different. So for the rectangular one is only 3, but for the hexagonal one is 1,500. But for the power loss, because the power loss is dust accumulation loss, so it means so many dust would fly to the solar panel. It will be an opacity point, so it cannot absorb the light or something. So the power loss is for the hexagonal one would be roughly 7 watts, and the rectangular one is 0.016. But for the activators, because like the folding part is 3 on each side, so we need the 6 activators to let it unfold. But for the origami one, we only need activator in the middle, like to give a torsion to it, then it will unfold. So it is the difference between each one. So yeah, and this is our reference. Thanks.
Come to the design where we have done the analysis on the tube set. What is actually, this is a hollow design, or it is a packed, how much weight it is having? You consider. What is the weight?
Weight. Here. 4.6 kilograms.
So is this tube set is hollow? Maybe you have made hollow structure?
Yeah, hollow.
Inside there is hollow structure?
Yes.
Only this is the
Only thickness for the shell, yes.
So how much is the thickness of the shell? Not mentioned. So which type of stress you have analysis? Static load?
Static, centroidal, and random. Which?
So why this direction we have made it load? Why you insist this direction?
Because the group say will develop like this way, like the head is here, and because the mainly load is from the air resistance, so air resistance will in the opposite direction between the to the velocity direction.
Or your solar panel will put some of the loading conditions to the CubeSat?
Because the solar panel will fold in the beginning and unfold in the
so
space.
Your conditions are only for building, not not for the other conditions.
Just launching process.
So launching process.
Yeah.
So all the conditions for your analysis only for the launching process.
Yes.
So you use vibration, you use there is sinusoidal vibration and no impact load analysis and anything, because it's the impact load is on launching after the deployment condition. Yeah. Do you use any buckling load calculation? Buckling? No.
Buckling, sorry.
Yeah, and look, it's also a load calculation analysis for buckling. It's like a bending.
No, we don't
No,
have
we
that.
don't have that. Actually, I test the horizontal because I think the horizontal will be uniform. So actually, the displacement will not.
So all these
change.
conditions are only for launching conditions. So whatever inside the vibrations in the launch rocket, only your CubeSat analysis on that end. There is a limitation. You have to mention the limitation on the report that it's only for launching.
Oh, okay.
Okay, sorry.
Yeah, that's okay. Your origami is good.
Okay.
That is a good one, which I think.
Thank you.
So more slides, or maybe you can add more thing on that. If you can do some analysis, if you have time, for like when the CubeSat is attached to the structure, and how much is the actual inside the stress with the attachment to the CubeSat. What will be the stress of that? If there will be some load on when deployed.
You mean when it is combined?
Combined together.
Okay.
Oh, okay.
Maybe some air resistance analysis only there. If the combined one, then it will be more good. Okay.
Thank you.
Thank you.
I think all have presented well. And so this is the end of the class. Now you have to present the report and share all your files in a folder which we will share you. So maybe all this comment you can incorporate in the report. Try to present it in a more beautiful way. Like Professor already told you, like abstract, literature review, what are the papers you have reviewed for this your project. Maybe you can put something about them and make a bibliography. So in the way like a research paper writing. So it will be helpful for you to understand how the paper can be written. Okay, thank you everyone.